All right, let's try this recording again. So the updated problem set 12 handout is just 5 seconds ago been put on the site. So it has a correct due date. And but the only one of the textbook exercises that's worth looking at from the point of view of a test is the very first one. So spring with no damping and no external force. But you see a practice problem on the test about that. A couple other quick items. Just a little shameless advertising, and also a reminder because I did this before. If you're in the process of signing up for classes for next semester, for math majors and even polymer science majors, I would encourage my upper level class, Math 460 Numerical Analysis 1, satisfies the technology requirement, or can be used as a upper level elective for either Math BS or licensure. I know Polymer Science has some courses that deal with numerical methods, so if you want something more in depth, the sequence 460 in the fall and 461 in the spring. Also, you get to be the first class to use my textbook. That's should be published this summer. So, all right, so that's the end of my shameless advertising. Also, on recent homeworks that I've been grading, I saw some situations where problems were simply, like reading questions in particular, were just left blank. If you're stuck, ask me. That's part of my job. That's what I'm here for. I don't know what hang-up is preventing you from doing that. Get over it. Okay, because it's again, the most frustrating thing I've experienced at this university for all 8 years I've been here, compared to the other 3 that I've taught at. This reluctance to seek help. Because if you take the time to do that, you might find not only getting some help with a problem, but also learning something more that can be helpful during the rest of the class. So don't just give up. That's not how learning works. So I did this all the time when I was a student. I would actually go to office hours. And it's something that made a big difference. Clears up some misconceptions. So I'm one of many resources that are out there that should be taken advantage of. Okay, now the focus for today, of course, is the test. So similar format to last time, where you're going to have a whole class period on Friday to dive into the test, and then I will collect them and look at them over the weekend. Give feedback, point out where you went wrong, or if you did the problem entirely right, and then give them back to you on Monday for the majority of the class period to fix things up. So what I'm going to do, this little exercise, it's spin on this teaching technique. It's called 1 minute paper, but I'm not having you write an essay, and we're going to take longer than 1 minute, because math can't be explained that quickly. So what I'm going to do is, pass these around. So it's a somewhat different format than the simulations of the first test that I gave the last time, where checking for speed. What I want to focus on now is, when confronted with a particular kind of problem, and I picked up 3 types of problems that show up on a test. It pretty much covers most of the test. These 3. Do you know how to get started? Do you have a coherent thought process for attacking these problems? When you get this, don't write your name on it just yet. Don't write anything down until I tell you. Okay. Okay, so the oh, hold on, one more to get back. So, all right, so the directions are there, but I want to just emphasize some things real quick. So all of the problems in the test except one fit into, or actually one or two fit into the form of one of the problems that you see here. This is actually something that was done way back when I was a student in a chemistry class I taught. But what the professor had us do was, he'd give us a problem and then say, write down in words how you're going to solve a problem, and then go ahead and do that. Because what happens a lot is, if you don't take time to think through these steps, what you end up putting it on paper, especially under time pressure from tests, can be really off the mark. So what I'm going to do is I'm going to aim for 5 minutes, and just write down, like, literally step-by-step procedure. 1, do this. 2, do this. And for each of these 3, you might not really have as good a handle, depending on how far you've gotten studying for the test. The last problem dealing with a spring, which we're going to talk about later today anyway. But I just want you to give it your best shot. And go. Yeah. Oh. Straight homework. Yeah. Right. Okay. Now, um, so I want all of these to be handed in. But before you start doing that, because I asked you to not write your name on it. Now that you've taken some time to try to answer these, um, it's optional for you to write your name on it. If you do write your name on it, because none of this counts for a grade or anything, what I will do is I will look over what you did and email you with any feedback on it in case your process is off or something like that. So, but that's your choice if you want me to do that. I still want to have all of them, name or not, just so I can see what's happening with the class as a whole. But so make your choice and hand them up.
You said it's 326 into the linear?
Yeah, 326. Okay. Yeah.
Was problem 0 there from homework set 11?
That's actually from 12. Yeah, well, 11 is on variation of parameters. Okay. Okay, any more? You got them all? Okay. All right, so those of you who wrote your names, I'll send something by tonight. Okay. Now, I imagine the one that would be most worth talking about is the spring one. So I'll just immediately jump to that, and then we can talk about the others as needed. So, okay. So the problem's going to have this form, and whatever you have in test will be of this form. So the constants m and k are needed. And you have some initial conditions. Okay. So the information that was given in this problem is that the equilibrium length, capital L, is 1 foot. And then we have the weight of the object is given to be 5 pounds. So if I'm going with English units, the equilibrium length is specified in feet, weight 5 pounds. Or in metric units, I might give the mass m in grams. Okay. Now we also have for determining initial conditions that is pulled down 6 inches from equilibrium and released. So that's one thing that can happen. The other possibility is that an initial velocity is imposed on the object from its resting position. Okay. So first let's deal with the constants because you need m and k, but you don't have either one. So can anyone tell me, so we'll list the first step, if m is not already given to you, then how would you get it?
Use the acceleration of gravity.
Use the fact that it's the weight that's given over v gravity constant. You're using this relationship, weight is equal to m times g, and you're just rearranging that to solve for m. Okay, so at least m is taken care of now. What about k? There's a relationship that k is involved in that now we would have enough information to solve for. What is that relationship? Yeah, KL minus mg is equal to 0. So your second step is to use whatever information you already have. So of course you just rearrange this to solve for k mg over L. So at this point, and if a weight is given to be 5, so it'd be, and then L is given to be 1 foot. We're dealing with feet, pounds, etc. So in this case, so it'd be 5 for that, and then the mass would be, the weight is 5, the gravity constant is 32. Okay, so now you have the constants m and k to put into your ODE. Questions about that part?
Where did you get the KL minus MG?
Okay, so that's a given relationship from for all these kind of problems. So that's something that just actually I want to check. Oh, sorry, I don't have my browser up because that messes with the recording. You're on my site?
Yes, sir.
Could you go pull up the practice test? I don't remember exactly what I put in the formula sheet. Okay. Yeah, the relationship is in the formula sheet. Okay. All right, thanks. Any questions about these steps? Yes.
Why don't we leave G in the formula?
What?
Why don't we leave G as part of the formula? When we're solving, we're plugging in, I guess.
Well, wait. First of all, which thing are you talking about? I
At the bottom, isn't that mg, k equals mg over L?
right. Why didn't I include it here? The thing is, mg is the weight.
Okay.
Yeah. Okay. All right. Okay, any other questions about getting the constants? Yes.
What is G in those units?
So the gravity constant for English units is 32 feet per second squared, whereas 9.8 meters per second squared for metric units. So know your gravity constants. Any other? Initial conditions. So can anyone tell me from these initial conditions where we have the object hanging on the spring at equilibrium position, but it's pulled down 6 inches more and been released. So if the effect is pulled down 6 inches, which initial condition is that going to influence?
U0.
What?
U0.
Yeah. So this tells me that U naught is equal to, be careful,
6 inches.
but what units are we in lengthwise?
0.5.
0.5. We're dealing in feet. You can use either one as long as you're consistent. Okay, so 0.5 feet. Okay. And the fact that it's released, well, how does that affect initial conditions?
0.
Yeah. So that tells us that the initial velocity is 0. Because you're pulling it down and then you just let go. So it's only the that extra displacement. So for instance, if it's already hanging at equilibrium, you don't do anything to it, it's not going to move. Both your initial values are 0. But alternatively, if it has equilibrium position, and then you give it an initial velocity, either up or down, keep in mind, in this coordinate system we use for these problems, down is positive. So for instance, if a problem states that it's given some initial velocity, like feet per second upward, that's going to be a negative value. We choose downward to be positive direction just because that's where to coincide with gravity. Okay. There's questions about the problem setup.
So then when we're calculating this, our G should be our negative 32 feet per second squared, right?
Well, the thing is, no, because we're going downward, then it becomes positive. So that it gives mg a positive value.
Okay.
So because we're pulling down, all the relevant constants in this problem are positive. So then, as far as how you solve a problem, at this point, once you have all this settled, then it's back to the first problem. You have some second order equation, linear equation of constant coefficients. So you do what done before. You get the let's see, characteristic equation. All right, so identify as the third step, handling the initial conditions. Then the next thing you should do is, for your characteristic equation, you have mr squared plus k is equal to 0, but m and k are both positive. So what kind of roots are you going to get from that? They're going to be complex because you have r squared is equal to minus k over m. So r is going to be plus or minus square root plus you have k over m I. So what is your general, and this value, you can abbreviate this as omega naught I, where omega naught is the natural frequency, square root of k over m. So what does your solution, your general solution, look like? What kind of functions do we have? Yeah, sine and cosine. So your general solution is a constant times cosine of what?
Cosine will be complex, right?
But yes, sine and cosine because it's complex. But cosine of what? Omega naught t. That's why we compute these. Whatever you get for your imaginary part of your root, and that's true in general, if you have complex roots, the imaginary part of your root goes in the argument to cosine and also sine. So your other term is c2 sine omega naught t. It's going to be one other problem on this test where you're going to get complex roots, so the same kind of thing is going to come up. All right.
Was the problem asking us to go this far?
Yes. Yeah. Well, in fact, it asks you to go. Well, there's 2 items more. Because after you do that, you use the just like in other problems, you find C1 and C2 using what? Initial conditions. I think I heard somebody say, or maybe it's wishful thinking on my part. Okay.
Do we not need the exponential values in our general solution? Or is that
Not here. Only in a problem that has damping. Would you have exponentials? But that's not going to be part of the problem on the test. So you're seeing this kind of situation. The only variation you could see is something different for initial conditions, like initial velocity instead of initial displacement. Or I give the information in metric units instead of English. So you're given the mass instead of the weight of the object. So once you find C1 and C2 using initial conditions, then you have your solution that describes the displacement of the object at time t. And then finally, okay. Checking my. Okay. So what the problem asks for is the these three aspects of the solution. Okay, 1 second here. Okay. So, like how you often describe like a sinusoidal curve, you have period, amplitude, and phase shift, and so what you need is okay. So the frequency is something that you actually already computed. That's your omega naught, square root of k over m. The period is going to be, it's just going to be 2 pi divided by that. Okay, so what is the length and time of one full cycle of the object as it oscillates on the spring? And then the amplitude, that comes from the constants. So the maximum height or depth of the wave that the motion of the object traces out is square root of c1 squared plus c2 squared. So once you have a solution, then all these three things come quickly. So that's as far as the problem goes. Because if you have this information, then it's easy to produce a graph of the displacement over time. No, I'm not asking you to do that, but it's something that could be done. Okay, so questions about working out one of these spring problems? Okay. Bless you.
Did we go over the number 6 on the practice steps?
Yes. Let's see.
Why is step 6 needed?
This is because the problem asks for most of that information. If you look at the wording of a problem, you'll see it's there. Okay, something is up here. I'm missing a page. Okay. I'll just pull it up here. Okay.
When is the linear algebra course? What time?
I don't know the time off the top of my head. Usually it's like in the afternoon, like a Monday, Wednesday, just historically. But okay, number 6.
That's what I was asking. Like, whenever I clicked it, it was only offered Bowling Corner late at night.
Oh yeah, we only have one section. Yeah, pretty much anything upper level there'll only be one section available.
So you were teaching it.
326? No.
Okay, so you're teaching 4-6.
Right.
That's the one. Okay.
Yeah. Oh, okay. Okay. All right. So number 6. Okay. Yeah, I kind of expected to be asked about this one. Okay. So here's a problem that does not have constant coefficients. All right, so you have ty double prime minus 2ty prime plus 2y is equal to 4t squared. And this asks for a general solution. There are no initial conditions. Now, and you're given 2 solutions of a homogeneous problem. Y1 is equal to t, and y2 is equal to t squared. So that information is essential for this. Now, it's a non-homogeneous problem. There are 2 approaches to solving a non-homogeneous problem, but only one of them can be used for this problem. Which one is it?
Variation.
You have to use variation of parameters. Now, so the first thing you do, isolate y double prime. Make the coefficient 1. So if there's something in front of y double prime, divide by it, because the solution formulas for variation of parameters depend on that. So we have y double prime minus 2y prime plus 2 over t y plus is equal to, and don't forget, common mistake, don't forget to divide the right-hand side by t also. So we have 4t. Oh, sorry, I goofed. That's supposed to be t squared in front. I only wrote a t. Okay, everything else is good. Okay, so I can divide by t squared. Okay, so now we just have 4 on the right-hand side. Okay. Last year. Does the season have allergies? Okay, now, so for your particular solution, it's going to have this form. It's going to be y1 w1 plus y2 w2. And then for w1, w2, you have formulas for those using integrals. So that's going to be minus the integral of y2, which is t squared, times g, which is 4. And be sure to use the g after you divide to make the coefficient of y double prime equal to 1.
What does that say above the t squared
Wait,
down there?
y2. I'm labeling the parts of a formula. And then below that you have the Wronskian of y1 and y2. So we need that. So the Wronskian of y1 and y2, that's the determinant of y1, y2, y1 prime, and y2 prime. I'll label the pieces here. Okay. So the determinant of that matrix is going to be what?
2t squared.
T squared.
T squared. Okay. So that's going to go down below. So we have 4t squared up top, t squared down below. There's always a lot of simplification that happens in these integrals, thankfully. Okay. So then you just get 4t for, minus 4t. Drop the minus. Okay. Can you tell me what part of the problem was causing difficulty, or?
Mainly going from the particular solution to the general solution.
Oh, okay. Yeah, because they have a similar formula for W2. So that's the integral of y1 times g over Wronskian. So that's going to be 4 over t. It simplifies to. So you get 4 natural log of t. So here's your W2, and here's your W1. So once you have those, you put them back into here, into this form. So your particular solution is going to be, okay, so y1, which is t, times w1, which is minus 4t, plus so y2, which is t squared, times w2, which is 4 natural log of t. And I think I can see where the question is coming from, because if we go ahead and simplify this, and then we have to add this to the solution, the general solution of a homogeneous problem. Oh, in case anything was missed by whoever's watching. Okay. Sorry, what?
I thought you said the bottom was the Wronskian.
It is. T squared. Okay. Your general solution generally is constant times y1 plus constant times y2 plus your particular solution. All right, so we fill in the pieces here. We get c1 times y1, which is t, plus c2 t squared, plus the particular solution is minus 4t squared plus 4t squared natural log of t. And you're probably wondering why a term was dropped, right?
Yeah.
Okay. Now, the thing is, that's actually an optional thing. Yeah. So if you go ahead and stop here, this is fine. In the interest of having a solution that's in as condensed form as possible, notice these are like terms. I can combine these. So I have c1t plus c2 minus 4t squared plus 4t squared natural log of t. So what do we have here? An arbitrary constant minus 4. Still an arbitrary constant. So I could just, that's why I can ignore this. Yeah. So it happens sometimes that terms pop up in your particular solution that have the same form as terms in your homogeneous solution. So in that case, go ahead and combine them, because that way, if there are initial conditions, you have fewer terms to work with. So again, it's an optional thing. So if you left it like this, I'd still give you full points. So up to you. Any questions about this one? One problem I definitely want to make a comment about is reduction of order. Because what you'll find on the formula sheet is very first item, if y1 is a solution, then here's the formula for the second solution, y2. That's what reduction of order is all about. Make use of that, because if you go through a laborious process of, okay, assume that y2 is equal to something times y1, you plug it into the original equation, simplify, get your first order ODE, solve that, etc., that's going to take you forever. So I'm offering you a time saver for reduction of order. So you definitely want to take advantage of that. In the last minutes that we have today, any other problems for practice test that you want me to talk about? Really? You're all set for this test. You're totally going to kick its butt on Friday. You won't even need Monday.
Oh.
Okay, well, I'll be around if further questions pop up. So those of you who were named down on the sheets, I'll send you something by tonight. So, okay, scram. Yeah.
I know I asked a question I pretty much written